start up. In our last class, we dealt with the concept of correlation analysis, and we defined correlation to be a concept, a statistical concept, a statistical method by which you can measure the relationship between two variables, say x and y. And we said there are tools and there are means by which you can measure this relationship. And one of which we discussed in the last class was called the scatter diagram. We said it's actually a graphical method of showing the relationship between two entities, say x and y, such that we tend to observe the direction in which the scattered point tends to move. Then we can now characterize the relationship between these two variables to be either perfect positive or perfect negative, or strong positive or strong negative, or weak positive or weak negative, or no correlation, depending on the direction of the plotted point. But this day we're going to be talking about Karl Pearson method of detecting a numerical value to the relation between these two variables, x and y. Now, Karl Pearson actually is a biometrician, a mathematician. He was the one that came up with a tool by which you can attach a numerical value to the relationship between x and y. Because all we have on the scatter diagram is just a graphical representation, so we could not assign a value to it specifically. But by the help of this biometrician, we're able to come to a conclusion, or come to deduction where we can actually assign values, numerical values to relationship. Then we can talk about, oh, this is strong positive and this is strong negative, or this is weak, this is strong. This is what Karl Pearson has actually supposed to do in its own methodology of solving for the relationship between two variables, say x and y. Stay with me. Of the relation between, say, variable x and y to be r. R means correlation x, y, which you can as well write as the correlation between, say, y, x, because it's actually symmetrical, to be equals to what? To be equals to the covariance between variable x and y, all over what? All over the standard deviation of, say, x times y. So this is the formula that we got from the concept of using the Karl Pearson means of getting a numerical value to correlation analysis. Now, with this, we can be able to assign values to them. But before then, this is not all. We can actually derive a formula that will look like this. From this formula, we can derive the formula, say R. Whenever you say R, it's implying rho, actually, telling us about a means, or telling us about the relationship that exists between two entities, two variables, x and y. Say, it's not necessarily, it could be P and Q, but conventionally I've been making use of x and y. So that's what R implies. So at the end, we should be able to come out with the formula, say, n summation x what xy minus the summation of what x, the summation of what of y, then all over the square root of what of in bracket n summation of x squared minus summation of what of x all in bracket squared, then n summation of y squared minus summation of y all in bracket squared. So this is what I'm going to be coming out with after we have been able to, from this junction, work some mathematical principle that we learn here. So we take a simple example to solidify the fact that this guy, called the Karl Pearson method, has the stature of bringing us into the realm of numerical value attached to relationship between two variables. Welcome back once again. Now, from the formula I gave initially, that R is given as what? As a covariance of the variables, say, x and y, from our basic statistics, the sigma of x and the sigma of y, implying the standard deviation of x and y. And we know from our basic statistics that our covariance of x y is what? The very summation of I from 1 down to n of x minus x bar and y minus y bar all over n. Meanwhile, our sigma of x is given as the square root of, say, the summation of x minus x bar squared all over n, and sigma of y is given as what? The square root of the summation of y minus what? Minus y bar squared all over n, with our x bar and y bar sustaining their what? Their natural meaning of mean. That means the mean value of x and the mean value of y. That's what we have our x bar and our y bar. So let us perhaps label this equation 1, which is our numerator perhaps, or let us call it equation 1, and let's call all of this equation what? 2, because this is our numerator and our denominator. Now let's try to, in a way, simplify this guy called the covariance. So in what way and what methodology can we use in simplifying that guy? So from equation 1, having the covariance of what? Of x comma y to be equals to what? The very summation of I ranging from 1 down to n of, then try to do your normal expansion where you have it to be, say, xy minus what? Minus xy bar plus what? Still minus x bar y, then plus x bar y bar all over what? All over capital N. This is what we add here. Then use the summation to expand all of it. Then you'll be having to see that the summation of x, y, your range sustained, minus what? Minus y bar, the summation of x, then minus x bar, the summation of what? Of y, plus the summation of x bar, y bar, all over n. Now, I know you know that our variable x bar and y bar they are constant. They are constant because they are already a numerical value. They are not the same as our x. X bar is not the same as our x, and our y bar is not the same as our y. The difference is that our y are variables, y and x are variables, y, x bar and y bar are what? Are constant. They are the mean of a given set of value. Meanwhile, I still want you to have it at the back of your mind that your x bar still sustain the mean, like I said initially, summation x over n, so that your summation x is actually equals to n x bar, and our y bar is seen as what? As summation what? Summation x all over n, so that summation y, I mean to say, all over x, so that our summation of y is equals to n y bar. So from this place, you can easily fix in the values here. Okay, but this Gaussian sustain is natural meaning of x, summation xy, minus y bar. And our summation x is actually nx bar. So I have it to be nx bar minus x bar, ny bar, like I have here, then plus n, summation of n x bar, y bar. So what do I mean by nx bar, y bar? What I mean to say that when you sum up a constant to n times, you are going to be having the n times that particular constant. So since x bar and y bar are constant, and we have our range really from I down to n, then you have it to be nx bar when it's being multiplied n number of times. Then all over what? All over our n. It's actually simple to relate to it. So at the very end, we're going to be having to be that the summation of x, y, these two guys are actually the same. It's just that the arrangement is different, but they are the same. So when I add this up, I can be having 2n x bar y bar, then plus what? Plus n x bar y bar all over what? All over n. So at the very end, you have this to be your summation of x, y minus 2 plus 1 is actually minus. So I have a minus n x bar y bar all over what? All over n. Actually, hopefully you are still with me. And okay, all over n. So we have just simply simplified this, our covariance of what? Of xy to be this. Please, I'm going to be keeping this so that we will not need to be writing this one again. So I have my covariance of what? Of xy to be equals to what? The summation of xy minus what? Minus n, and the summation of x bar y bar. Meanwhile, before I go on, I believe you know that I could easily factorize n from this place. When I factorize n from here, I'll be having, there is no n, yes, I'll be having n. Okay. Okay, let me not factorize n for now, so I won't complicate matters for my viewers. So just say all over what? All over n, and we stop here. So as we go further, let's try to simplify this as well as this. Then we do our final computation. Welcome back once again. Now, as we continue the class, we have our what? Our sigma of x to be equals to what? The very summation, the square root of the summation of what? Of x minus x bar squared all over what? All over n. Then I try to simplify this as I can as well. What am I going to be having? Just your normal way of expanding your bracket, which is simple. I know you know that it's going to be what? The summation of open bracket x squared, then 2 times this giving you minus 2x x bar plus x bar squared all over what? All over n. Then from here, what you have next is that you just simply open your bracket with your summation symbol, and we have it to be what? The summation of x squared, having this number range of 1 to n, minus 2x bar summation of x plus the summation of x bar squared. Does that make sense to you? Sorry, there's supposed to be squared here and not outside. So all over n. So on that note, I believe you know that we'll be having the square root of, say, the summation of x squared minus, you know our summation x sustained nx bar, so I have it to be 2x bar nx bar plus nx bar squared all over n. Now, summation of a constant with n time gives us n there actually. So, and in a long run, I'll be having the square root of what? Of the summation of x squared minus 2x minus 2n x bar squared plus n x bar squared all over n. So that at the very end, I'll be having it to be, say, the square root of, say, that the summation of s squared minus nx bar squared all over n actually. So, and you recall, I believe you still remember that my x bar is the summation of x all over n. And because you can remember that, then I believe you can easily relate to the fact that the square root of this guy, of the summation of x squared minus n, open bracket, summation of x all over n, all bracket squared, all over n. Are you still good? I believe it's comprehensive. So I have the square root of the summation of what? Of s squared minus n, the summation of x all bracket squared, all over n squared, all over n. So at the very end, one n can actually take away another n, and when I try to bring out n concept, n values, so I'll be having it to be that the square root of, when I bring out n, I'll factorize n from this entity at the numerator, I'll be having n coming out, so that I'll be having, pardon me please, when I bring out, when I bring out 1 over n, that's what I mean to say. When I bring out 1 over n from here, I'll be having, open bracket, n summation x squared minus summation x all in squared, and close the bracket, extend this guy a bit, so that I'll be having it all over n actually. So at the very end, I'll be having to be that the square root of what? The square root of of n summation of what? Of x squared minus summation of x all in bracket squared all over this n times n. So I have n squared because of the division symbol. It turns over to becomes a multiplication. I have n squared. And finally, you know that this will fetch us the square root of what? Of n summation x squared minus summation of x all the bracket squared, so that this square root will be limited to the numerator all over n, since the square root of n squared is just n. So we arrive at this. So in the same vein, when you go through for that of the sigma of y, following the same method, you'll be having it to be n summation y squared minus summation y all bracket squared all over n. So we don't need to go through the same process, through the same stuff, since we're already changing the symbol. Nothing is changing, the steps are still the same. So you can try completing that yourself and be sure you arrive at something like this, only that you'll be having y squared here and y here. Welcome back once again. Now, we have been able to validate the fact that sigma of x is equal to the square root of what? Of n summation x squared minus the summation of x all in bracket squared all over n just as the sigma of y would also be the square root of n summation y squared minus what? Summation y all in bracket squared all over n in the same vein. Meanwhile, we have our covariance to be of x and y to be equals to the summation of what? Xy minus n x bar y bar all over capital N. But we can actually still simplify this, as you can see, that it can become the summation of xy minus n, summation of x over n, summation of y over n, all over n. How do you have this? I know you know that x bar is summation x over n and y bar is summation y over n. So a1n takes a1n, and when you try to factorize 1 over n out of that equation, I have 1 over n in bracket. Here will be n summation xy minus summation x summation what? Y. Then all over what? All over n, like we have it here. And I believe you can easily relate with. Then at the very end, we have to be n summation of y minus summation of x y, I mean to say, minus the summation of x summation of y all over and n squared. So let's quickly see what we can do in our journey of trying to compute this that we have on the board. I know you know that our R is covariance of x and covariance of x, y. Meanwhile, instead of writing that, you can write this now, since this is the simplification of that. So I have it to be my n summation of xy minus summation of x summation of y all over capital n squared, I mean to say, then all over. Now your sigma y sigma x is same thing as what I have here. So instead of what we writing that, we just write this here straight. So we're having the square root of what? Of n summation x squared minus summation what? X all in bracket squared times the square root of what? N summation y squared minus summation y all in bracket squared, then all over n all over n. So by which it's becoming clear, by simple simplification, we'll be having that to be R equals to n summation xy and summation of x summation of y all over what? N squared times, now this is times now, times this will give us n squared. So n squared just flips off by the principle of multiplication, and I have sustained my summation of x squared minus summation of x all in bracket squared here times the counterpart of y, summation of y squared minus summation of y all in bracket squared. So this n squared takes away n squared. And by the principle of indices, where I believe in that a raised power half times b raised power half will just give us a raised power what? A b raised power what? Half equally. So we can easily say that what? We can easily say that R equals to n summation of xy minus summation of x summation of y all over the square root of what? Summation of x squared minus summation of x all in bracket squared, then summation of y squared and the summation of please pardon me, there is n at the back here. Please do not forget that there is n at the back of this guy, and there's also a n at the end of this back. So that at the very end, I'll be having my n at the back here, and I have my n summation of y here. So summation of y all in bracket squared here. So that we have this. So this implies we are going to be assigning a numerical value of saying that xy having a particular value. We can now assign a value to it, because this is what the capacity method tends to do: assign a numerical value to the relation that is between the variables, say x and y, and it's actually symmetrical, like I said from the very beginning of the class. Now our variable r has a scale of measurement. What do I mean by scale of measurement? Is that our variable r actually range in between 1 and minus 1. It implies that if our r is equals to 1, it implies the perfect positive relationship that we discussed in our scatter diagram of our previous class. And when r is equals to minus 1, it implies the perfect negative relationship. But it has this grouping, it has this way of saying that when our r is in between strictly less than 1 and perhaps is 0.1 0.9, thereabout, 0.8, we refer to it as strong positive. And if it was between minus 0.8, I mean to say that, okay, minus 1, strictly less than r, and less than or equals to minus is 0.8, we call it strong positive. Then, strong positive. But when it is around 0.5, to be less than or equals to r, less than 0.8, they call it the moderately positive. When it is the negative counterpart, is called the strong positive, so the moderately positive. But when it is actually less than 0.5, strictly less than 0.5, and it's around strictly less than 0 as well, they call it around the weak positive. And same thing when it is for the negative address too, is called the weak negative. But the moment our r is actually equals to 0, it is called non-linear relationship between the variables. Okay, but let me submit to you that various books have various way of grouping these stuffs. Some still refers to 0.7 as strong positive, and from 0.5 to around 0.6 they call it as moderately positive, and if it is negative aspect 2, we call it as moderately negative relationship. Do you understand? So it depends on the book you are looking into for analysis. Meanwhile, let us take one example to justify what I've been discussing since the beginning of the class. Now, I believe you know that in any entity, between any entity we see, a relationship exists. Perhaps not necessarily a linear relationship. Some can have other type of relationship that is beyond the scope of this class. But we are actually looking at the concept of the linear relationship. We know there's a relationship between our height and our weight. There's a relationship between our income and expenditure. So let us assume that we have a variable x and we have a variable y depleting anything. But let's, in this essence, let's deplete, let's say that the scores of male and female in the class. What is the relationship? Okay, let's say that in a maths class, which is over 10 marks, over 5 marks, I mean to say, some girls scored 2, and the guy scored 3. Here is 3. It's 3. Here is 4. Here is 1. Here is 3. Here is, let's say, 2. Here is 5, and perhaps here is 1. Let's try to see if we can detect the relationship between these two. So all you need to do is just to complete our table, and I believe you know that we are going to be filling out this table with the variable needed, like our variable xy, our variable x squared, our variable y squared. Do you understand? So find our variable xy. This gives us 6, this gives us 9, this gives us 4, this gives us 6, this gives us 5. And our s squared will give us 4, 9, 16, and 9 with 25. Then our y squared will give us 9, 1, 4, and 1. That is squaring each entity in this place. That is what gives us our y squared. Then if you can perfectly recall our formula of r, which is given as what? As n summation xy minus summation what? X summation y, all over what? All over the very square root of what? Of n summation x squared minus summation x, all in bracket squared, and n summation y squared minus summation y, all in bracket squared. Then you can easily know that we still need the concept of the summation of x and y. So when I try to sum them up, what do I have? So 2 plus 3 is 5, plus 4 is 11, sorry, 5 is 9, 9 plus 3 is 12, and this is actually 17, and 3 plus 3 is 6, plus 1 is 7, so 7 plus 2 is 9, and this is actually 10. Then 6 plus this is 15, plus 4 is 19, 25, and this is 30. Then 4 plus this is 13, 13 plus this is 29, and 29 plus this is 38, and 38 plus this is 63. Then 9 plus 9 is 18, plus 1 plus 2 is 20. Then I have it to be 24. So with this, I am good to go with my computation. So that my R and my N, you know, is just what? 1, 2, 3, 4, 5. There are 5 observations here. So because of that, we can just simply compute our N to be what? 5 times the summation xy is 30 minus summation x is what? Summation x gives you what? Gives you 17 times Summation y gives you 10 all over what? All over the very big square root of what? Of 5 times your s squared is 63 minus, times. So minus your summation x squared is 60, summation x I'm going to be 17 squared. So I have it to be 17 squared, close the bracket, then 5 times summation y squared, which gives me 24 minus summation y between 10 squared. So at that very end, I have 150 minus what? 170. So over the square root of what? Of 15, 315 minus 17 squared is 289 all in bracket. Then I have it to be 24, 22, 120 minus 100. So I have it to be like my r is what? Is minus 20 all over. When we subtract this, what do we have? We have a positive numbers, 15 minus 8 is 6. Then I have it to be 3 here, then that is 26 times in bracket 20. So at that very end, what do I have? I have minus 20 all over. When this is multiplied, I have the square root of 520. 520. So when it's being multiplied, I have 520. So, and my r is then equals to, we have minus 20 actually, all over the square root of 520. So I'll be having minus 0.877. Now with this, what does that imply? It implies that there's actually a strong negative relationship between these two variables. Now let's try to depict that using a simple scatter diagram. We then deplete what we really have. If there was our x-axis and there's our y-axis, and our y is from 1, 2, and range from 1, 2, and 3. 1, 2, and 3. We don't actually convey what we have here is 0. And here is from 1 to 5. 1, 2, 3, 4, and 5. So when we have 2, 3, 2 on the x-axis and 3 here, what do we have? We have it here. Then we have 3, 3 here, and 3 here. Then we have 4, 1. I have 4 here, and I have a 1 here. Then I have 3, 2. I have 3 here. I have 2 here. Then I have what here? I have 1, 5. I have 1. 5, 1. 5 here and 1 here. Now, if you can see, if you just fix a straight line, you will discover that this line is coming in a negative direction. But looking at it, we cannot attach a numerical value to it. But this has helped us to detect that our r is simply minus 0.877 by number. So thank you for being a part of the class. And please do not forget to subscribe. Thank you.